Start recording. There we go. Let's make sure we got sound happening. Yes, we do. That's good. Okay. So, have you guys heard of electrolytes? In what context? Yes?
In energy drinks?
In energy drinks. Okay, so they will have them in an energy drink, although you don't really need them in an energy drink per se. Usually they're used after working out very hard in the heat because they will replace your electrolytes. Exactly, just like that one right there. And those electrolytes are things like sodium, ions, potassium, calcium. Okay, there's some phosphate, things like that in there. And they are found in Gatorade, they're found in your body, they're found in seawater and in batteries and in plants. They're found like virtually in all living things, okay? And they are handy because they conduct electricity but not in the same way that a wire conducts electricity, but they do it due to the presence of freely moving ions. Because basically what current electricity is, you need to have the movement of charged particles. And if you have, say, a copper wire, what are the charged particles that are moving in the copper wire? What moves in a copper wire for it to be a current electricity? You guys don't know? Yes, you do. Electrons. Okay, so in the copper wire, it is electrons that flow. Okay? Now, there's lots of substances that conduct electricity, but they don't have any free electrons. However, conduction of electricity does not require freely moving electrons. It just involves freely moving charged particles. And so instead of electrons, we can use, what are some other particles that we know that have charges? Protons, but protons are stuck in the nucleus and they're unable to move. What are some other charged particles? Ions. Okay? So there are solutions that conduct electricity, and they do not have freely moving electrons, but they do have freely moving ions in solution. So if we take a look at this little device here, we have a battery. And we have a wire. And we have a stick of metal. That's called an electrode. And we have another stick of metal. That is our other electrode. Did you guys get book 8? Yeah. Okay. Now, if you imagine that there was no beaker here, okay, so imagine we had no beaker and there was no solution, there were no ions, no nothing. If we just had the two electrodes, the wire and the battery, kind of sitting like this, would current flow? No, because we don't have a complete circuit, yes? Right? If these are the electrodes, they're not touching, right? So you would have to make them touch in order to have a complete circuit. We can also complete the circuit, though, by adding this beaker full of ions. Okay, so here we have, and that's hard to read that. I'm going to relabel that. That is an electrolyte solution. And an electrolyte solution conducts electricity due to the presence of what? Have a chat with your partner about that. What's in that beaker that's allowing electricity to be conducted? Ions, okay? And not just any old ions, but freely moving ions. So what you can see in here is that we have our battery, and we have the positive terminal here. What does a positive terminal do to the electrons in the wire? Yeah, it attracts the electrons in the wire. So you can see that the electrons are like, yeah, let's go this way. Look at that positive. It's so beautiful. Okay. And then we have the negative terminal over here. What does that do to electrons? It repels them. So off they go. Okay, so we end up with a positive charge over here, right? And a negative charge over here because the electrons are going in here. And what is going to happen to these ions that are dissolved in the solution? What are the positive ions going to do? They're attracted to the negative. So the cations are attracted to the negative electrode. So that's why every time you see like a little positive, we have arrows pointing that way. And I would have drawn more, but it gets really messy. Yeah? Now, what about our negative ions? What do they do? Yeah, our anions are attracted to the positive electrode. So we have completed the circuit. We're allowing for these negative ions to move towards the positive and neutralize that, and the positives move toward the negative. Now, to be fair, what really happens at this point is that the extra electrons in here actually don't build up at all. They actually transfer onto the cations and then make them neutral. Yeah? And these anions over here will actually give their electrons to neutralize those positive charges. But we don't have to worry about that this year. Basically, as long as you get the idea that electrons are moving, if electrons are moving counterclockwise, right, then the anions will also be moving counterclockwise, right? The cations are going to move in the opposite direction. They're going to move clockwise. And then we have a complete circuit. Okay, and that's why we call it an electrolyte, because it conducts electricity. All right, and how do you get this solution with freely floating ions? What do you have to dissolve in water? You either have to dissolve, yes? An ionic compound, and the other one that gives you ions is? Acids. Do you remember how to tell if you have an ionic compound? What does it begin with?
Metal.
A metal, or who's the polyatomic ion? The polyatomic cation? Ammonium. Okay, so that you know you can get an electrolytic solution if it starts with a metal or with ammonium. You can also get it if you have an acid. How do you know you have an acid? Starts with hydrogen. Okay, so on our next page, we have that. We've got how can we get an electrolyte? You can have a dissolved salt. In other words, ionic compounds. So they begin with a metal or ammonium. Or you can have a dissolved acid, which those are molecular compounds or covalent compounds. But they also dissociate into ions in solution, which is, yes, a little bit weird, but that's okay. And acids start with H, or they end in COOH. So basically, if you're like, do I have an electrolyte? Well, the first thing you have to ask yourself is it aqueous? Because what if I gave you solid sodium chloride and I attached my electrode here and my electrode here, and this was the battery? Would this conduct electricity? I've got positive, negative, positive, negative, positive, negative, positive, negative. This is sodium chloride crystal. Chat with your neighbor about that. Will this conduct electricity? So, yes or no? No, why not? The ions are not free to move. They are locked in this crystal lattice structure. You would have to either melt it or dissolve it. Okay, so solid ionic compounds are not electrolytes. So this is not an electrolyte. However, if we dump it into water, what do those ions do? They dissociate, and we get our dissociation equation. And now those ions can move around as much as they like, okay? Now, just to remind you about our dissociation equations, when you finish a dissociation equation, you should always have ions. Yes? So we have a charge here of plus, and we have a charge here of minus. That is different from decomposition. What would the decomposition of sodium chloride look like? NaCl would become Na, solid, and Cl2, gas. Okay, so just bear in mind, it's different from decomposition. This is a physical process. This is chemical. Okay? I didn't balance this, but there we go. Okay. Okay, and here we have aqueous acids. And once again, the ions, what do? They dissociate. Dissociated free-moving ions. And therefore we have an electrolyte. Okay, and again, we've got H plus and we've got Cl minus. Whenever you have a dissociation, you should have ions at the end. Now, what if we took a covalent compound, or in this case, we're not going to do a covalent compound, we'll do a covalently bonded element, because if we have I2, if we have an I and another I stuck together, what's holding the two atoms together? What's holding I to I? That's a covalent bond. Okay, and you can see over here, we have a little iodine molecule and another iodine molecule, right? So I'm just going to draw two of them over here so we can sort of zoom in on it a little bit better. Okay, so here's another iodine molecule. What is going on in between the iodine molecules? What is holding them together as I2 solid? Intermolecular forces, yes. So when we take our solid I2 and we throw it into the water, do the covalent bonds break? No. Okay, the covalent bonds stay intact, and it is only the intermolecular forces that break. So when iodine dissolves in water, our IMFs between the I2 molecules break, and then we actually get, if I had like a little water molecule here, I would have some IMFs in between the two. Yeah? Little IMFs. So we would form new IMFs between the I2 molecules and the water. So we get new IMFs between the I2 and the water. But the strong covalent bonds stay intact. And we don't call this process dissociating, we call it dispersion or dispersal. So if I said to you, okay, school's over, disperse, what would you do? You would all scatter in all directions, yes? Well, theoretically, unless you're walking home together or whatever. Okay, so that's basically disperse. And you can see that in our dispersion equation, we start with I2. What do we finish with? We finish with exactly the same. The only thing that has changed is the state. So we have these lovely free-floating particles. Are they charged? I2, does it have a charge? No. No charge. And therefore, this is a non-electrolyte. So if you have any molecular compounds other than acids, those will be non-electrolytes. So covalent molecular solutes are non-electrolytes. And that's as far as I got with my other class. So I told them they have no homework tonight. You're just to have a good Halloween. All right. And that's it for today.